So in previous examples, we've seen how to put different groups on a benzene ring. A halogen like bromine, an SO3H group, a nitro group. We can put all of those on benzene now. We've seen the mechanisms. Starting with this mechanism, we can do something really exciting, and that is form a new carbon-to-carbon bond to a benzene ring. You could take any carbon chain and add a benzene ring onto it. Think of the power of that. Benzene often acts as the functional part of a molecule. It's the part that fits into a receptor site in living things. And you can take the benzene rings in other molecules, in known medications or known psychoactive medicines or any type of medicine. You can take the known benzene rings in those and attach them to any carbon chain you want, with any type of solubility, with any type of acidity or basicity. And so you really gain a lot of power in creating medications and creating medicines by being able to attach benzene rings to different carbon chains. The type of reaction that allows you to do that is called a Friedel-Crafts reaction. So you see it here, Friedel-Crafts. And it's named after the two scientists who developed it. Oftentimes, the mechanism for creating new carbon-to-carbon bonds is named after the scientists who invented it because it's such a significant thing to contribute to humanity, to contribute a way to form new carbon-to-carbon bonds. So you've seen Grignard reagents, the Diels-Alder reaction, now you're seeing the Friedel-Crafts reactions for ways to form new carbon-to-carbon bonds. Now the mechanism for this is actually really similar to the mechanism for bromination. We're going to use a metal catalyst, much like we did before. And we also are going to have at least one halogen on the carbon chain that we want to attach to benzene. Okay, so we're always going to have some sort, so the recipe for this, you'll always have some sort of carbon chain. Remember, in organic chemistry, a capital R is like an X in math. X in math means any number. Capital R in organic chemistry means any carbon chain. You'll always have some carbon chain, and it'll be attached to a halogen. Usually the halogen is chlorine. You'll have a metal catalyst, like AlCl3, and you'll have benzene. Those are the three ingredients you need to mix together to whip up these pancakes. Now, we're going to draw this mechanism 3 times. The first time, the R group will be a cyclohexyl group, it's like a cyclohexane ring. The second time, it'll be a tert-butyl group. And the third time, it will be this carbon chain, a sec-butyl group. Well, a little bit longer than that. It'll be a different carbon chain. In all those cases, though, you have a carbon chain with a chlorine on it. And that's that first ingredient in this recipe, a carbon chain with a chlorine on it. The other two things are always a metal catalyst and benzene. So let's get down to it. In bromination, sulfonation, and nitration, we saw the first step is always to form a really strong electrophile, because benzene is a nucleophile, but because it's aromatic, it's so stable, so it's a terrible nucleophile. And to get it, you have to entice it to react by luring it with a really reactive electrophile. So in this case, to turn these carbon chains with chlorines on them, these alkyl halides, into strong electrophiles, we combine it with this metal catalyst. And the metal catalyst is going to do a similar thing here as it did in the case of bromination. Anytime you see a metal in organic chemistry, you want to think, that metal has such low electronegativity. It's going to give its electrons away and become slightly positive. And whatever atoms it's bonded to, those will become slightly negative. Now in this case, the aluminum is slightly positive, and it's bonded to 3 atoms, and it has no lone pairs around it. So the shape of this molecule is trigonal planar. It's trigonal planar. And so it's flat, like a pancake. And the chlorine on the carbon chain that we want to attach to benzene, that chlorine is able to sort of descend onto the top of this pancake and get close to the aluminum. Chlorine, much like bromine, is a really big atom. The halogens in general, all of them except for fluorine. Fluorine's about the size of hydrogen, so it's very small, which is why we don't see it very often, but chlorine is really, really big. Chlorine, bromine, and iodine, all the halogens except for fluorine are really big. That's why they were such good leaving groups. It's also why they're polarizable and they're good nucleophiles. Because they're so big, there is a lot of room on any side of the chlorine. And if the chlorine gets close to this aluminum chloride pancake, it can feel the positive charge on the aluminum, and all the electrons in the chlorine atom can get close to that aluminum. There's plenty of room. They get close to the aluminum without being close to each other. Compare that with what would happen if it were small. If it were a small atom, if all the electrons tried to get close to the aluminum, they'd all have to be close to each other, and then they'd repel each other, and so they couldn't all get close to the aluminum. But the fact that the chlorine is so big means all those electrons can get close to the aluminum, and that side of that chlorine atom becomes slightly negative, and the other side of the chlorine atom becomes slightly positive, so that you have this dipole, these two ends, positive and negative ends, on an atom, the chlorine atom. And so the side that's close to the aluminum ends up becoming nucleophilic, and so it can attack the aluminum. So let's draw that in without the whole atom and the picture of what's happening in the chlorine included. The chlorine gets close to the aluminum, all the electrons rush to one side, and so the electrons end up attacking the aluminum. So you form this really high energy intermediate. You have the cyclohexane ring, attached to the aluminum. The aluminum is still bonded to 3 other chlorines. This chlorine has a positive charge, and the aluminum now has a negative charge. Now, this is a very unstable molecule. This is going to crumble apart really fast, and it can crumble apart in a couple ways. First, the electrons can go back to the chlorine. That's the first thing that can happen, but then we just end up with our reactant, so that would have no net effect. But another way that they can crumble is the electrons on the other side of the chlorine can go to soothe that positive charge. You have this electronegative element with a positive charge. It's ravenously searching for electrons. And so it's going to steal them from anything close by. If it steals it from the right, you end up with a reactance, it's equilibrium. But if it steals it from the left, then you get a new thing. Not just any new thing either. If it steals the electrons from the carbon on the left, then you end up with your carbon chain having a full positive charge. You have a carbocation there. And that is going to be your awesome electrophile. The electrophile with such a big positive charge that even benzene will attack it. You also have the aluminum. The aluminum is bonded to 4 chlorines, and the aluminum has a full negative charge, so this is pretty unstable, right? All the electrons in these bonds are repelling each other, so they're all trying to push each other off the molecule. Aluminum is a metal. It doesn't have a lot of electronegativity. It's not able to hold them on together, and so this is going to crumble too. We'll see the role that plays, how that crumbling affects the reaction after benzene attacks. So far, it should resemble, if you know the mechanism for bromination, you should see a lot of parallels so far. One word to the wise. You have here a carbocation intermediate. And what you should remember from Organic Chemistry 1 is that carbocation intermediates can rearrange. Carbocations are always bonded to just 3 things. That's why they have their positive charge. You could have that positive charge, you could have the carbocation bonded to just one other carbon, in which case that carbon can donate its electrons and help stabilize it. That's primary. hydrogen doesn't have as many electrons to help that out with. You could have the carbocation bonded to two other carbons, in which case they both could help donate their electrons to stabilize it, and that's secondary. Or you could have your carbocation bonded to three other carbons, in which they all could help donate electrons to stabilize this, and that's tertiary. So tertiary carbocations are more stable than secondary carbocations, which are more stable than primary carbocations. And atoms will rearrange, either hydrogens or methyl groups will rearrange to create more stable carbocations. So this is something you have to consider in this reaction, this Friedel-Crafts alkylation reaction that we're doing. Anytime you form a carbocation, you have to worry about the carbocation rearranging. So we'll see an example of that in a couple, not in this mechanism, but in a couple mechanisms from now. For this one, this carbocation, if you look at this, is secondary. This is bonded to two other carbons. And next door, this is also secondary, and this is also secondary. So all of the positions nearby have the same stability as this, and so the carbocation doesn't rearrange. So anytime you're doing Friedel-Crafts alkylation, you have to worry about this carbocation rearrangement. Look at the atom that has the positive charge on it, see whether it's primary, secondary, or tertiary. Look at each of the carbons next door, see if it's primary, secondary, or tertiary. And if it's more substituted next door, if one of the carbons next door is bonded to more carbons, then you'll have a carbocation rearrangement. The positive charge moves to the more stable place. Okay, so much for that side note, that quick refresher of Organic Chemistry 1. And if you are interested, I have whole videos that go in detail about carbocation rearrangement, so email me and I'll be able to send you links for those. For now, we have our awesome electrophile, and so benzene can swoop in and attack. We have our nucleophile. Nucleophile attacks our amazing electrophile. And what we get at first when we do this, I'm going to just put this hydrogen here so we can keep track of this. What we get at first when we do this is we have our benzene ring. Oops. Those electrons in the pi bond are used to form a new bond, and the new bond will be to our carbon chain, which here was a cyclohexane. Now, this carbon had those pi electrons. They were taken away, and so now this has a positive charge. But that positive charge, as we've seen previously, is allylic, and so we have resonance. So warn the world that you have resonance by drawing those brackets and writing those special resonance arrows that tell you to take the average of all the molecules within the brackets. The true structure never looks like any of these molecules we're about to draw. It always only looks like the average of them. Okay, well, we've talked about in the previous mechanisms for bromination, sulfonation, and nitration, having that allylic positive charge means you have parallel p orbitals on more than two atoms, and so the electrons spread out over that whole area. And so it's not right to call this a double bond and this a single bond. Instead, we have to draw resonance arrows to show how they're both in between bonds. When you have an allylic positive charge one atom away from an atom in a double bond, the pi electrons move toward the positive charge to create a new bond. So you end up with a molecule that's really similar. But the electrons move, they stabilize that positive charge, and you get new positive charge at the bottom. That is now allylic to the other side, and so to draw the intermediate bonds there, you draw the pi electrons going toward the allylic positive charge, And in that case, the positive charge gets stabilized, the electrons move, and you have a new positive charge here. So we've seen this in the mechanisms for bromination, sulfonation, and nitration before. This resonance stabilized intermediate is the sigma complex. And it lowers the activation energy for the reaction. You don't need as much energy to destabilize this stuff because the sigma complex is relatively stable because of how the charge is spread out through this resonance. But it is more unstable than our reactant because we've destroyed aromaticity. And so we just need to restore aromaticity using a base. And that's where this metal catalyst comes back into view. All of these chlorine electrons, all the bonds there are pushing each other apart, trying to kick each other off the aluminum. And aluminum is a metal. It's not very electronegative, so it's not able to attract the electrons to itself and keep those chlorine atoms on. One of the chlorines gets pushed off. Now you can choose any one you want. I'm going to choose this one on the left. It takes its electrons, the electrons in the bond, it takes these electrons and it uses those to steal the hydrogen. The electrons to the hydrogen end up going to restore the aromaticity. And so you end up with your benzene, which is now aromatic. Oops. And it has the cyclohexane on it. And now these two became HCl. It's not that big of a deal. And then you have the aluminum with just 3 chlorines again. And the significant thing about that, notice, is that is what we started with. We started with AlCl3. So it's a catalyst. It's a molecule that helps the reaction to happen but doesn't get used up. That's a catalyst. So the net effect is we added this whole carbon chain onto the benzene ring with this Friedel-Crafts alkylation. Just a word about the word alkylation. Alk is referring to a hydrocarbon chain. If you add any hydrocarbon chain to a benzene ring, it's called alkylation. So you're just adding some hydrocarbon chain to the benzene. So Friedel-Crafts alkylation. Now I went through the steps there, but with that specific molecule, we're going to go through all those steps with 2 other molecules, and you'll see that they're really the same thing. So I'm going to go through it faster for these other molecules because the steps are really the same, so it's a repetition of what we've seen so far. But let's just review. You have some carbon chain with a halogen on it. It creates this high energy intermediate, which ultimately creates an awesome electrophile. Benzene attacks the electrophile, forms a resonance stabilized sigma complex, and there's a base that comes by to restore the aromaticity. So you end up with a carbon chain now on your benzene ring. Okay, so what would Friedel-Crafts alkylation look like if this were your carbon chain? Well, in this case, you would react this with aluminum trichloride. The aluminum is slightly positive because it's a metal, very low electronegativity. The chlorines are slightly negative. This chlorine is slightly negative, but also when it gets close to the positive charge on the aluminum, all the electrons in the chlorine go towards it, rush towards it because the chlorine's so big and polarizable, and it attacks the aluminum. We get our first intermediate. The chlorine has a positive charge, the aluminum has a negative charge. This molecule crumbles. The electronegative chlorine steals the electrons from the opposite side, and you end up getting an amazing electrophile, this carbocation, and you end up getting this pretty unstable intermediate. And this is unstable because this aluminum, this metal with low electronegativity, is forced to keep track of a lot of electrons and keep that negative charge. You form a carbocation, you have to worry about it rearranging. Notice that this carbon is bonded to 1, 2, 3 other carbons. That makes it tertiary. Each of the other carbons is just bonded to 1, so they're all primary. And a tertiary carbocation is more stable than a primary carbocation, so that carbocation is going to stay exactly where it is. Oops. So we don't have to worry about carbocation rearrangement there. So now we can draw our benzene, which is our poor nucleophile, and we can have it attacking that amazing electrophile. Remember, there's a hydrogen on each of those carbons. And we end up getting our resonance stabilized intermediate. We have the 1, 2, 3 carbons. Now they're attached to the benzene. But the pi bond there, the electrons in this pi bond went to form this new bond. So the carbon next door has the positive charge, and that positive charge is allylic to the pi bonds. So the pi bond goes toward the positive charge to give you the next resonance structure. When it moves over, you have your second resonance structure with the positive charge at the bottom. That's now allylic to the other pi bond, which goes towards it to give you your third resonance structure. Those are our three. All right. When that moves towards it, it neutralizes the positive charge there, but now you have a positive charge here. And let's not forget this hydrogen that was there this whole time. And so this is our resonance stabilized sigma complex. And that resonance helps to stabilize that intermediate, but that intermediate is still relatively unstable because it destroyed the aromaticity. And so a base comes in. We talked about how these electrons all repel each other. They push one of the chlorines off with its electrons. It takes those electrons, steals the hydrogen, and the electrons there go to reform the aromaticity. So you end up with the benzene ring regains its aromaticity, and you have the tert-butyl on it. So we have tert-butyl benzene. We also have HCl, which isn't such a big deal, but also significantly we have, after this fourth chlorine comes off, we have AlCl3, which is what we started with, and so that is our metal catalyst, that molecule that helps the reaction to happen but doesn't get used up. That is a catalyst. And so we made this new bond to a carbon. We put a carbon branch onto a benzene ring. Or you could flip it and say it the other way. We put the benzene ring onto a carbon branch using this Friedel-Crafts alkylation. So that was B. Let's see this applied with just one more molecule. And this one will be interesting because this one will have a carbocation rearrangement. The first step is to combine this with your metal catalyst to turn this into an amazing electrophile. The aluminum is a metal, so it has very low electronegativity. It gives its electrons away and becomes slightly positive. The chlorines steal those electrons and so become slightly negative. This chlorine is also slightly negative, for sure, and the carbon is slightly positive. So it's an okay electrophile, but we want to turn it into an amazing electrophile. Furthermore, the chlorine is gigantic, so it's polarizable, and when it gets close to the aluminum, all the electrons rush to that side, it becomes a better nucleophile, and it attacks the aluminum. You end up forming this intermediate. The aluminum has a full negative charge, chlorine has a full positive charge. That molecule is going to crumble fast. The way that it crumbles to continue the reaction is the electrons away from the aluminum go onto the chlorine. Remember, the electrons toward the aluminum could have gone into the chlorine, but that would have just brought us back to the beginning. So we have that happening in equilibrium, and sometimes instead of that happening, the electrons on the opposite side go onto the chlorine. So that would leave you with two molecules. First, this carbocation, and then this unstable intermediate for the metal catalyst. And now that we have this carbocation, we have to think about rearrangement, carbocation rearrangement. Anytime you have a carbocation, always consider carbocation rearrangement. This carbon that has the positive charge on it is bonded to one other carbon, so it's primary. It only has one carbon next door, this one right here. That's bonded to 1, 2, 3 other carbons. So that is tertiary. A tertiary carbocation would be more stable than a primary carbocation. So you have what's called a hydride shift. One of the hydrogens on this molecule picks up its electrons and takes them over to the carbocation. Notice, curved arrows show the movement of electrons. You would never show a curved arrow moving the positive charge. You have to show electrons moving to where the positive charge is, and that recreates a new positive charge. So instead, you would have this new molecule you have the hydrogen here. But remember, in these skeletal structures, you don't always draw the hydrogen, so you could put that in or you don't have to. It doesn't matter. So that's what we have right now. That's our awesome electrophile at the most stable carbocation. And so now we can react that with benzene. Benzene is our weak nucleophile that can attack this strong electrophile. Let's keep track of this hydrogen on this benzene carbon. And what we end up with there is we have the hydrogen, and now we have this. Now let's think about this. This carbon is this one here. It's going to have 2 methyl groups and 1 ethyl group. So that's our branch. That's our carbon chain. When these electrons attacked that electrophile, they formed this new bond. The electrons used to be on this carbon here, but they're not there anymore, so that lost electrons, that has a positive charge now. Because that positive charge is allylic, as we've seen many times before, it's going to give rise to resonance. And when you have an allylic positive charge, the pi bond goes to form a new bond toward the positive charge. You draw all the resonance structures in brackets, and in between them you draw those special resonance arrows that tell you to average all the molecules inside the brackets. So here that pi bond moves over. You get a new positive charge at the bottom. That's allylic to your other pi bond. So that other pi bond moves over. Between each of the resonance structures, you have this double-headed arrow. So the electrons move over, and when they do, they stabilize the positive charge, but then a new positive charge arises. So this is your resonance-stabilized sigma complex. And so that resonance helps to make that intermediate more stable, but of course it's less stable than benzene. Benzene was aromatic. And so we need some sort of a base to come in and steal this hydrogen and restore the aromaticity. And that is where our catalyst comes in. All of the electrons here are repelling each other. They're trying to push one of the chlorines off. One of the chlorines takes its electrons, leaves that molecule, steals the hydrogen, and the electrons that were going to the hydrogen go to restore aromaticity. So now you are left with your molecule, your benzene ring, attached to a carbon chain. And you also have HCl, that's not the biggest deal. And you also have what's left, AlCl3, aluminum trichloride. And that's what we started with, so that's really a catalyst. It helps the reaction to happen, but it doesn't get used up. It's reproduced at the end. So ultimately the result is that we took that carbon and we attached it to a benzene ring, or if you want to think about it the other way, we put this benzene ring onto a carbon chain. In any event, we took a feature, a molecular feature that's very biologically active, and we put it onto a carbon chain that we could have done anything to before. We could have made it very polar, very non-polar, very acidic or basic. And so we take this biologically active, medicinally useful feature, and we make it able to dissolve in tissues that have whatever properties this other chain has. So that's Friedel-Crafts alkylation. It's a really significant reaction. You can see that the mechanism is very similar to bromination. It's just instead of two halogens, you have one halogen and a carbon chain. And you can see how the mechanism is really the same no matter what the carbon chain is. The one thing to watch out with these, very common mistake, is to forget the carbocation rearrangement. So if you don't feel comfortable with that, send me an email. I'll send you a video that goes into carbocation rearrangements in detail. But otherwise, this is the Friedel-Crafts